This presentation is delivered by the Stanford Center for Professional Development.
Okay, so thank you for coming out in the rain. I appreciate trudging over here and risking your health and life. So I'm going to do a little diversion here to explain this idea of functions as data before I come back to fixing the problem we had kind of hit upon at the very end of the last lecture about set. So what I'm just going to show you is a little bit about the design of something in C++ that is going to be helpful in solving the problem we'd run into. What I'm going to show you here is two pieces of code, right, that plot a single valued function across the number line, right? So in this case, the functions that the top one is doing is plotting the sine function, right? The sine wave, right, as it varies across, and then the square root function, right, which goes up, kind of has a sloping curve to it. And that both of these have exactly the same behaviors, right? They're designed to kind of go into the graphics window, and they're just using kind of a very simple kind of pen moving strategy. Like it starts at a particular location based on what the value of sine is here, and then over a particular interval at 0.1 of a 1/10 of an inch, it plots the next point and connects a line between them. So it does a simple kind of line approximation of what that function looks like over the interval you asked it to plot. The same code is being used here for plotting the square root. And the thing to note, and I tried to highlight by putting it in blue here, was that every other part of the code is exactly the same except for those two calls where I need to know, well, what's the value of square root starting at this particular x? So starting at value 1, what is sine of 1, what is square root of 1? And as I work my way across the interval, what's the square root of 1.1, 1.2, 1.3, and sine of those same values? And so everything about the code, right, is functionally identical. It's kind of frustrating to look at it, though, and realize, wow, if I wanted to plot a bunch of other things, I also want to be able to plot the cosine function or some other function of my own creation, right, across this interval, that I keep having to copy and paste this code and duplicate it. And so one of the things, right, that hopefully your 106A and prior experience has really heightened your attention to is, if I have the same piece of code, in multiple places, I ought to be able to unify it. I ought to be able to make there be a plot function that can handle both sine and square root without having to have to distinguish it by copy and pasting. So I want to unify these two. And so there is, the mechanism that we're going to use is kind of follows naturally, if you don't let yourself get too tripped up by what it means, is to imagine that the parameters, for example, going into the function right now are the start and the stop, the interval, from x is 1 to 5. What we'd like to do is further parameterize the function. We'd like to add a third argument to it, which is to say, and when you're ready to know what function you're plotting, here's the one to use. I'd like you to plot sine over the interval start to stop. I'd like you to plot square root over that. If we added the third argument, which was the function we wanted to invoke there, then we would be able to unify this down to where we had one generic plot function. The good news is that this does actually have support features in the C++ language that let us do this. The syntax for it is a little bit unusual, and if you think about it too much, it can actually make your head hurt a little bit to think about what it's doing. But you can actually use a function's name, and the code that is associated with that name as a piece of data. That not just, the code, you think of the code as oh, we're calling this function, we're moving these things around and executing things. The things that we tend to be executing and operating on, you think of as being integers and strings and characters and files. But you can also extend your notion of what's data to include the code you wrote as part of the possibilities. So in this case, I've added that third argument that I wanted to plot. And this syntax here that's a little bit unusual to you, and I'll kind of identify it, is that the name of the parameter is actually fn. Its name is enclosed in parentheses there. And then to the right would be a list of the arguments or the prototype information about this function, and on the left is its return value. So what this says is you have two doubles, start and stop, and this third thing over here isn't a double at all. It is a function of one double that returns a double. So a single valued function, right, that operates on doubles here. That is the syntax in C++ for specifying what you want coming in here is not a double, not an array of doubles, anything funky like that. It is a function of a double that returns a double. And then in the body of this code, when I say fn here, where I would have said sine or square root or identified a particular function, it's using the parameter that was passed in by the client. So it says call the client's function, passing these values to plot over the range using their function in. And so the idea is that valid calls to plot now become things like, well, plot, and then you give it an interval, 0 to 2, and you give the name of a function. The sine function, which comes out of the math library, the square root function, also in the math library. It could be that the function is something you wrote yourself, the my function. In order for this to be valid, though, you can't just put any old function name there. It is actually being quite specific about it, that plot was defined today, it took a double, returned a double. That's the kind of function that you can give it. So any function that has that prototype, so it matches that format, is an acceptable one to pass in. If you try to pass something that actually just is some other kind of function that doesn't have the same prototype, so the get line that takes no arguments and returns a string, just doesn't match on any front. And if I try to say, well, here, plot the get line function over the interval 2 to 5, it will quite rightfully complain to me that just doesn't make sense. That's because it doesn't match. So a little bit of syntax here, but actually kind of a very powerful thing, and it allows us to write to, in addition to kind of parameterizing on these things you think of as traditional data, integers and strings and whatnot, to also say, as part of your operations, you may need to make a call out to some other function. Let's leave it open what that function is and allow the client to specify what function to call at that time. So in this case, for plot, what function that you're trying to plot, let the client tell you, and then based on what they ask you to plot, you can plot different things. All right, way in the back.
Is there a similar setup for multivariable functions?
Certainly. So all I would need to do, if this was a function that took a couple arguments, I'd say double, comma, int, right? If it returned void, it returns. And sometimes it looks a little bit like the prototype, kind of taken out of context and stuffed in there. And then those parens around the function are a very important part of that, which is telling it, okay, yeah, this is a function of these, with these prototype information. Behind you. No, you're good now. Somebody else over here.
Is that fn a fixed name?
No, it's like any parameter name, you get to pick it. So I could have called it plot function, my function, your function, whatever I wanted. Here in the front.
Is this only in C++ or does like Java?
So Java doesn't really have a similar mechanism that looks like this. C does, right? So C++ inherits it from C. There are other ways you try to accomplish this in Java, right? It tries to support the same functionality in the end, but it uses a pretty different approach than a functions as data approach. Okay.
Can you pass like a method, like an operator?
So typically not, right? This syntax that's being used here is for a free function, a function that's kind of out in the global namespace at that level. There is a different syntax for passing a method, which is a little bit more messy, and we don't tend to need it, so I won't go there with you, but it does exist. It just, as it stands, this does not want a method, it wants a function. So method meaning member function of a class. Okay, so that was just to kind of set the groundwork for the problem we were trying to solve in set, which was set, right, is holding this collection of elements the client is stuffed in there. It's a generic templated class, right, so it doesn't have any preconceived notion about what's being stored. Are they strings? Are they student structures? Are they integers? And that in order to perform its operations efficiently, it actually is using this notion of ordering, keeping them in an order so that it can iterate in order, it can quickly find, on the basis of using order to quickly decide where something has to be if it's present in the collection. So how does it know how to compare something that's of unknown type? Well, what it does is it has a default strategy. It makes an assumption that, well, if I used equals, equals, and less than, that would tell me kind of where to go. And so it's got this idea of it wants to know, well, given two things, are they the same thing, in which case it uses kind of the zero to show the ordering between them. If one precedes the other, it wants to have some negative number that says, well, this one precedes it, or some positive number if it follows it. And so it applies this operation to the types that are there. And for strings and ints and doubles and characters, this works perfectly well. And so that's how, without us going out of our way, right, we can have sets of things that respond to the built-in relational operators without any special effort as a client. But what we can get into trouble with, right, is when equals, equals, less than don't make sense for type. So let me just go actually type some code, and I'll show you. I have it on the slide, but I'm going to, wow, this chair suddenly got really short. See if I can do that. Okay. We'll go over here, because I think it's better just to see it really happening. So I'm going to ignore this piece of code, because it's not what I wanted. But if I make some student T structure, and it's got the first and last name, and it's got the ID number, and maybe that's all I want for now, that if down in my main, down to find my main, there it is. I'm going to need that piece of code later, so I'm going to leave it there. If I make a set, and I say, oh, I'd like to make a set of students, my class. And I do this, and so I feel like I haven't gotten out of trouble yet. I made this this structure. I say I'd like to make a set of students. Each student is in the class exactly once, right? I don't need any duplicates. And I go through the process of trying to compile this. It's going to give me some complaints. And its complaint, which is a little bit hard to see up here, right, is there's no match for operator equals equals in 1 equals 2, and operator less than in 1 equals 2. And so it's kind of showing me another piece of code that's a little bit of a hidden piece of code I haven't actually seen directly, which is this operator compare function. And that is the one that the set is using, is it has this idea of, well, what's the way it should compare two things? It says, well, I pass into this operator compare that works generically on any type of things using equals equals and less than. And if I click up here on the instantiated from here, it's going to help me to understand, well, what caused this problem? The problem was caused by trying to create a set who was holding student T. And so this gives you a little bit of an insight into how the template operations are handled by the compiler. That I have built this whole set class, and it depends on there being equals equals and less than working for the type. The fact that it didn't work for student T wasn't a cause for alarm until I actually tried to instantiate it. And so at the point where I said I'd like to make a set holding student T, as the first point where the compiler actually goes through the process of generating a whole set class, the set angle bracket student T, filling in all the details, kind of working it all out, making the add and contains and whatever operations, and then in the process of those things are making calls that try to take two student T objects and compare them using less than and equal equals. And that causes that code to fail. So the code that's really failing is kind of somewhere in the class library, but it's failing because the things that we're passing through and instantiating for don't work with that setup. So it's something we got to fix, right? We got to do something about. Let me go back here and say, well, what am I going to do? What am I going to do? Well, so there's my error message, same one, right? And it's saying, yeah, you can't do that with a struct. Well, what we do is we use this notion of functions as data to work out a solution for this problem. That if you think about kind of what's going on, the set actually knows everything about how to store things. It's a very fancy, efficient structure that says, given your things, keeps them in order, and it manages to update and insert and search that thing very efficiently. But it doesn't know, given any two random things, how to compare them, other than this assumption it was making about less than and equal equals being the way to tell. If it wants to have sort of a more sophisticated handling of that, what it needs to do is cooperate with the client. That the implementer of the set can't do it all. So there's these two programmers kind of that need to work in harmony. So what the set does is it allows for the client to specify by providing a function. It says, well, when I need to compare two things, how about you give me the name of a function that when given two elements will return to me their ordering, this integer 0, negative, positive that tells me how to put them in place. And so the set kind of writes all of its operation in terms of, well, there's some function I can call, this function that will compare two things. If they don't specify one, I'll use this default one that maps them to the relationals, but if they do give me one, I'll just ask them to do the comparison. And so then as it's doing its searching and inserting and whatnot, it's calling back. We call that calling back to the client. So the client writes a function. If I want to put student T's into a set, then I need to say, well, when you compare two student T's, what do you look at to know if they're the same or how to order them? So maybe I'm going to order them by ID number. Maybe I'm going to use their first and last name. Whatever it means for two things to be equal and have some sense of order, I write the function, and then I pass it to the set constructor. I say, here's the function to use. The set will hold on to that function. So I say, here's the compare student structure function. It holds on to that name, and when needed, it calls back. It says, okay, I'm about to go look for a student structure. Is this the one? Well, I don't know if two student structures are the same. I'll ask the client. Here's two student structures. Are they the same? And then, as needed, go keep looking, insert and add and do whatever I need to do. So let's go back over here. I'll write a little function. So the prototype for it is that it takes two LMTs and it returns an int. That int is expected to have a value 0 if they are the same, and a value that is negative if the first argument precedes the second. So if A is less than B, you return some negative thing. You can return -1 or -100 or -1,000,000, but it needs to return some negative value. And then if A, B, and some orderings, they're not equal, be later, it will return some positive value, 1, 10, 6 million. So if I do, let's say I use ID num as my comparison. Okay, based on whether nums are the same, if they are, I can return 0. And if ID num of A is less than the ID num of B, I can return -1, and then the other case I'll return 1. So it will compare them on the basis of figuring that the name field at that point is nothing new. And then the way I use that is over here when I'm constructing it, is there is an argument to the constructor, and so that's how I would pass an argument to the constructor, add parens to the name as I'm declaring it, and then I pass the name. Did I call it compare student or students? I can't remember. Call it compare student, okay. And this then, so now there's nothing going on in the code, causes it to compile, and that if you were to put, let's say, a cout statement in your comparison function just for fun, you would find out as you were doing adds and compares and removes and whatnot on this set, right, that you would see that your call kept being made. It kept calling back to you as the client saying, I need to compare these things, I need to compare these things, to decide where to put something, whether it had something, and whatnot. And then based on your ordering, right, that would control, for example, how the iterator worked. That the smallest one, according to your function, will be the one first returned by the iterator, and it'll move through larger or sort of later in the ordering ones until the end. So it's a very powerful mechanism that's at work here, because it means that for anything you want to put in a set, as long as you're willing to say how it is you compare it, then the set will take over and do the very efficient storing and searching and organizing of that. But the only piece you need to supply is this one little thing it can't figure out for itself, which is, given your type of thing, how do you compare it? So for the built-in type string and int and double and char, it does have a default comparison function, that one that was called operator compare. Let me go open it for you. It's actually sitting in the 106. So there is a compare function.h, and this is actually what the default version of it looks. It's actually written as a template itself that, given two things, right, just turns around and asks the built-in operators to help us out with that. And that is the name that's being used. If I open the set and you look at its constructor call, I had said that I would come back and tell you about what this was. That the argument going into the set constructor is one parameter whose name is CMP function that takes two elem type things. So here's one of the example of the two argument prototype, returns an int, and then it uses a default assignment for that of operator compare, the one we just looked at, so that if you don't specify it, it goes through and generates the standard comparison function for the type, which for built-ins will work fine, but for user-defined things is going to create compiler errors. So you can also choose if you don't like the way the default ordering works. So for example, if you wanted to build a set of strings that was case insensitive. So the default string handling would be to use equals, equals, and less than, which actually does care about case. It doesn't think capital Apple is the same as lowercase. If you wanted it to consider them the same, right, you could supply your own. Write a compare case insensitively function, took two strings, converted their case, and then compared them. And then when you establish a set of strings, instead of letting the default argument take over, go ahead and use your case insensitive compare, and then now you have a set of strings that operates case insensitively. So you can change the ordering, adapt the ordering, whatever you like for the primitives, as well as supply the necessary one for the things that the built-ins don't have properties for. So then that's that piece of code right there. All right, so it makes sense? Well, now you know kind of the whole range of things that are available in the class library. Right, so we saw the 4 sequential containers, the vector stack queue, and the grid that do kind of indexed ordering and kind of allow you to throw things in and get them back out, right? We went through the map, which is the sort of fancy heavy lifter, right, that does that key value lookup, and then we've seen the set, which does kind of aggregate collection management and very efficient operations for kind of searching, retrieving, ordering, joining with other kind of sets and stuff that also has a lot of high utility. I'm going to do one quick little program with you before I start recursion, just because I think it's kind of cool, is to talk a little about this idea of once you have these ADTs, you can solve a lot of cool problems. And that's certainly what this week's assignment is about. It's here are these tasks that if you didn't have, so ADTs, just a reminder, I say this word as though everybody knows exactly what it means, is just the idea of an abstract data type. So an abstract data type is a data type that you think of in terms of what it provides as an abstraction. So a queue is this FIFO line. And how it works internally, what it's implemented as, right? We're not worried about it all. We're only worried about the abstraction of NQ and DQ and it coming, first in, first out. And so when we talk about ADTs, we say, well, once we have a queue or a stack or a vector, we know what those things do, what a mathematical set is about. we build on top of that. We write code that leverages those ADTs to do cool things without having to also manage the low-level details of where the memory came from these things, how they grow, how they search, how they store and organize the data, that you just get to do really cool things. So you probably got a little taste in the Indiana 106A when you get to use the array list and the hash map to do things. This set just kind of just expands out to fill out some other niches where you can do a lot of really cool things because you have these things around to build on. So one of the things that happens a lot is you tend to do layered things, and you'll see a little bit of this in the assignment you're doing this week, where it's not just a set of something, it's a set of a map of something, or a vector of cues, a map of set. And so I gave you a couple of examples here of, oh yeah, the things that might be useful, right? Like if you think of what a smoothie is, it's a set of things, mixed together, some yogurt and some different fruits, right? Some wheatgrass, whatever it is you have in it. And that the menu for a smoothie shop is really just a bunch of those sets. So each set of ingredients is a particular smoothie they have, and then the set of all those sets, right, is the menu that they post up on the board. You can come in and order. The compiler tends to use a map to keep track of all the variables that are in scope. As you declare variables, it adds them to the map so that when you later use that name, it knows where to find it. Well, it also has to manage, though, not just one map, but the idea is as you enter and exit scopes, right, there is this layering of open scopes. So you have some open scope here, you go into a for loop where you open another scope, you add some new variables, right, that when you look, it actually shadows, right, that at the nearest definition, so if you had two variables of the same name, it needs to look at the one that's closest, and that when you exit that scope, it needs those variables to go away. And no longer be accessible. So one model for that, right, could be very much a stack of maps, where each of those maps represents the scope that's active, a set of variable names and maybe their types and information is stored in that map. And then you stack them up. As you open a scope, you push on a new empty map, you put things into it, and then maybe you enter another scope, you push on another new empty map, stick things into it. But as you exit and hit those closing braces, right, you pop those things from the stack to get back to this previous environment you were in. So let me do a little program with you. I just have this idea about how this would work, and we'll see if I can code something up. So I have, let's go back over here. I am going to, this is the piece of code that just reads words. So that's a fine piece of code to have here. I have a file here. Let me open it up for you. That just contains the contents of the official Scrabble Players Dictionary edition 2. It's got a lot of words in it. It's pretty long. It's still loading. Let's go back and do something else while it's loading. Okay. It happened to have about 120,000 words, I think, is what it is in there right now. So it's busy loading, and I have this question for you. Right? There are certain words that are anagrams of each other. Right? The word cheap can be anagrammed into the word peach, right? Things like that. And so I am curious, for the official Scrabble Players Dictionary, so if you imagine that some words can be anagrammed a couple times in 5 or 6 different words just by how you can rearrange the letters, I'm curious to know what the largest anagram cluster is in the official Scrabble Players Dictionary. So I'd like to know across kind of, all 127 words, 27,000, that they form little clusters, and I'd like to find out what's the biggest of those clusters. Okay, so that's my goal. Okay, so here's what I got going. I have something that's going to read them one by one. Okay, so let's brainstorm for a second. I want a way to take a particular word and kind of stick it with its other anagram cluster friends. What's a way I might do that? Somebody help me design my data structure. Help me out. A little louder. I've got the word peach. Where should I stick it so that I can...
You could, as you say, you could treat each string as like a set. Or
so I have this string, right, which represents the letter. So I've got the word peach, right? I want to be able to stick peach with cheap, right? So where should I stick peach in such a way that I could find it? And you've got this idea about, well, the letters there are a set. They're not quite a set, though. Be careful because, for example, the word banana, right, has a couple A's and a couple N's. And so it's not that I really want it to come down to be the set BAN, right? I wouldn't want to coalesce the duplicates on that. So I really do want to preserve all the letters that are in there. But you've got your idea is getting us somewhere. It's like, well, there is this idea of kind of like, for any particular word, right? There's the collection of letters, right, that it is formed from. And somehow, if I could use that as an identifier in a way that was reliable. Anybody got any ideas about what to do with that?
We did that as a vector for each letter and then the frequency of each letter in the word.
So I could certainly do that, right? So I could build kind of a vector that had kind of frequency, so I'd have this little struct that maybe was character and the number of times it occurs, right? And then I could kind of try to build something on the base of that vector that was like, well, here is, do these two vectors match, right? So does banana match, apple? And you'd say, well, no, it turns out, they don't have the same letters. I'm trying to think of a really easy way to represent that. So your idea is good, but I'm thinking really lazy. So somebody help me who's lazy.
Could you have a map where the key is like all the letters in alphabetical order and like the value is like a vector of all the...
That is a great idea. That's a great idea. You're taking his idea and you're making it easier. You're capitalizing on lazy, which is, I want to keep track of all the letters that are in the word, but I want to do it in a way that makes it really easy, right, to for example, to know whether two have the same, we'll call that the signature. The signature of a word is the letter frequency across it. If I could come up with a way to represent the signature that was really easy to compare two signatures quickly to see if they're the same, then I will have less work to do. And so your idea is a great one. We take the letters and we alphabetize them. So cheap and peach, right, both turn into the same ACE, HP, right? It's a nonsense thing, but it's a signature. It's unique, right, for any anagram. And if I use a map where that's the key, then I can associate with it every word, right, that had that same signature. So let's start building that. Let's start building it. So let me write the, I'm going to call this the signature. That given a string, it's going to alphabetize it. So let's say I'm going to write the dumbest version of this ever, but I'm just going to use a simple sorting routine on this. So smallest is going to small index. We'll call it min index. That's a better name for it. Min index equals I. And then I'm going to look through the string and I'm going to find the smallest letter that's there and move it to the front. Is basically going to be my strategy. But that's the wrong place to start, though. I'm going to look from I to the 1. Okay. So if S sub j is less than S sub min index, so it is a smaller letter, then the min index gets to be j. Okay. So far what I've done is I've run this loop that kind of starts, in this case, on the very first iteration. It says, well, the first character in slot 0, that must be the min. And then it looks from there to the end, is there anything smaller? Whenever it finds anything smaller, it updates the min index. So when it's done, after that second loop has fully operated, then min index will point to the smallest alphabetically character, right? The smallest alphabetically character in the string that we have. And then I'm going to swap it to the front. So we'll do this S sub I with S sub min index. Okay. And I'll write a swap, because swap is pretty easy to write. So let's see about how we do this. Okay. So if I like how this works. And then let me stop and say, right here, now is a good time to test this thing. I just wrote signature. It probably works, but then again, it's potentially could not. And I'm just going to show you a little bit of like how I write code. This is good to know. As I say, I put some code in here that I plan on throwing away. Enter word. And then I throw it through my function. Oh, I think I called it signature, didn't I? Signature S. So the idea being, if it doesn't work, I want to find out about this sooner rather than later. It doesn't like my use of getLine. Is that because it's not included? Yes, it's not. So let's go get the right header files. This is half the battle sometimes, is figuring out what headers are needed to make your compiler happy. So now it's up here and I enter a word and I say, yeah, what does cheap come out as? It goes into the debugger. That's good. So it wasn't right. Now we're going to get to find out. What does it not like about that? It says, wow, did we forget to return something? Let's go look at our code. So it's complaining about this, oh yeah, I can see where we're going to get in trouble here. It's complaining at the return. It was saying that, I'm trying to print something and it looks like garbage, that what I'm trying to print didn't make sense at all. And I could say, well, that's funny. Let's go look at signature.
Did you want to pass the parameters?
Ooh, that's probably a good idea. We ought to fix that while we're there. But hey, let me leave that bug in for a minute because I'm going to fix my first bug and I'll come back to that one. So it turns out what it's really complaining about though has to do with, I said, well, what does signature return? So somehow what's being returned by signature is being interpreted as total crap when it got back to main. And there's a very good reason for that because I never returned anything. And so maybe if I had been less cavalier about the fact that it was giving me a warning over here that said control reaches the end of non-void function, but I was being lazy and I didn't look, was that I didn't pay attention to the fact. So let's leave my other bug in that you've already pointed out. But because this is exactly what it's like when you're doing it. You enter words and you say cheap, and it says cheap. And you're like, no. And you're like, well, how about and? Hey, look, that's in alphabetical order. And then you spend all your time thinking of words that are in alphabetical order for a while. You're like, well, tux, that's in alphabetical order. And you're like, it seems to work. You can do that for a while, but then you're like, this whole cheap, not good, not good. Okay, so I come back here. My friend, who's already a step ahead of me, right, has pointed out that my swap is missing the all-important pass-by reference. That as it is, right, it was swapping the copies that got passed to the function, but of course nothing was happening back here in signature land. So if I fix that, and I come back in here, I'm going to feel better about this. Oh my gosh, and even tux still works. And if I say banana, I should get a bunch of A's, a bunch of B, and an N. So there's various cases to kind of test out if you have multiple letters, and if you have letters that are the same letters, if you have, apple, that it doesn't lose your duplicates and seems to come out right. And so given this, right, the word peach, right, should come down to the same signature as cheap, and so that seems to indicate we're on the path toward building the thing we wanted to build. So I have this read file thing that I'd left over from last time that reads each word, and I'm going to change my vector into a map of set of string. What capitalization do you not like? Yeah, so it turns out this file happens to all be lowercase, but you know what? There's no harm in doing this, right? And that way, even if they weren't, right, it'll now take care of that problem for us if we wanted it to. What do we want lowercase? Oh, yeah, I do. Well, yeah, case. You guys are so picky. Okay. All right, here's my deal. I'm going to take my map, and this is going to be a line of code that's going to make your head spin, but just go with it. Okay. This is the do all craziness. Okay, so I've got this map, and what I want to do is under the signature of this word, I want to look up the set of strings that's associated with it and tack this one in. And the add, in this case, right, with the set, I know that's going to do non-duplication. In fact, the file doesn't contain duplicates, but if it did, I certainly don't want it to record it twice anyway, so I might as well do this. Now, this form of this is a heavy lifter, right, for a small piece of code. That the signature then, went and converted it into the ACEHP form. I use that as the key into the table. If it was already there, it's going to retrieve to me an existing set that I'm going to go ahead and just add a word onto. If it wasn't there, right, the behavior for the brackets is to create kind of a new empty value for that. So to use the key and then kind of create default value for type. Well, the default value for set of strings, so if you just create a set without any other information you need in the default constructor, will always create you a nice, clean, empty set. So in fact, it will get me exactly what I want, which is put it in there with an empty set that I will immediately add the word into. So after I do this, I should have this fully populated map, and then I'm going to do this just as a little test. I'm going to say num words when I'm done, to feel a little bit confident about what got put in there. Oh, well, how about I call it? That's a good idea. It's so fussy, so fussy. C++ never does what you want. Okay. I think I called this thing ospd2.text. It has the words in it. And then I need to declare the variable that I'm sticking all this stuff into. It is a set. Okay. So go in, load stuff, doing its thing. The number of words, 112,882. Okay, that's close enough. I can't remember the number that's in there, but that sounds like a fine approximation of it. And so I feel like it did sort of manage to do something for it. And I can actually do this, right, if I were just, want to get a little glimpse into it, is to use my iterator to look at something that's in there. Wait, it's the map of set of string, iterator. And while iter.hasNext, I'm going to say key equals iter.next, and I'm going to print that key, and I'm going to print the size of the set, because I'm at this point okay. You should see gobs of printing coming out of this thing. Takes it a little bit of while to process the thing, and then see gobs and gobs of stuff going by. It looks like a lot of things are ones, if you can imagine kind of reading them as they go by, because a lot of words are really just not anagrams of anything else. But some of the shorter ones have sort of a better chance. Okay, so you can find out here at the end that they're EEIKLPEST. I don't know what that is. Leakiest? No? I don't know what that word is. I can't actually invert any of them. I'm like, this dictionary has a bunch of really crazy words in it too, so it makes it especially challenging. You're like, what is that? I don't know. That one almost looks like beginners, but it's got an F in it. Well, it's the F beginners. A very famous word. You guys probably have heard it. Okay, so I've seen that, and now I want to do the thing where I'm saying, well, what's the largest one? I'd like to know. Somebody should tell me. Int max size and string max key. So I'll set this to be 0. The max key is that. And then I'm going to do this. If the size of this key is greater than my max size, then it's going to get to be the new key. Okay, so after I did all of that, then max is, so I have my max key, and then I probably want to see what they are. So why don't I go ahead and take a look. Oh, I have to be able to type though. It equals m of key, max key, I guess, dot iterator while it has next, cout it.next and no. Okay. So it went back, it found the maximum, in this case using the size of the sets as the distinguishing feature. And then the max is AEPRS, which it's got a big old list of like about 12. 2, 3, 4, 5, 6, 7, 8. That's 12 actually, maybe 13. So now you know. You can impress your friends at parties. This is the kind of thing you can win bar bets on. Oh yeah, what's the size of the largest anagram cluster? And so everybody wants to know this kind of stuff. I can't believe you guys can sleep at night without actually knowing this. And what's neat to know, though, just to point out a couple of things, right? That we could use a little decomposition in this code, but that there's a kind of very small amount of things we're having to do, right? For example, like one of the things that's really powerful, things like the map, right? Where you're like, oh, if I can just figure out how to key the things to store the collection right under that key, that then looking it up and adding something, right, is a very efficient sort of direct operation, just building on these things and then it going through and doing all the work of storing them, sorting them, making it efficient for us to retrieve them and look them up such that I can process 100,000 words, right, in the blink of an eye, and then go back through, look at them all, find the biggest one, get my information out.
When you make the call to m.size, is that the number of words?
That is the number of keys, unique keys.
Right, so it's not actually the number of.
Yeah, so it doesn't know anything about everything else that was stored, but it does. In fact, that's why it's often. Well, I know the dictionary has about 127,000 words. It turns out they form about 112 unique signatures, right? And so there's actually another 20,000 words, right, that are clumbed onto some existing signatures. So in fact, that is the number of unique signatures across a dictionary, not really the number of words. So that's the wrong name to call that.
For the M signature word thing where you said the default is just to create a new stack. That works as well for vectors and cubes.
Yeah, it works for anything who, if you were just to declare one on the stack, does the right thing happen? And so vectors, set, maps, all those things do. But the primitive types, like int and double, it doesn't, right? So it would work for string. String is an empty string, So for sort of the fancier, sort of, more modern types tend to actually know how to just default construct themselves into a good state. But the primitives don't do that. And so if you were having a map of ints and you wanted to have them start at 0, you need to really start them at 0. Like you can't call just m sub this. It will be garbage, and you will just be operating with garbage from that way forward. All right, well, we're good. All right, what I'm going to give you is the 8-minute discussion of recursion that whets your appetite for the things we're going to be doing next week. Okay. So recursion is one of those things I think that when you haven't yet had a chance to explore it firsthand and other people tell you about it, it has sort of an awe-inspiring sort of mystery, some fear and whatnot. And so first off, I want to kind of shake that fear off. It is a little bit hard to wrap your head around the first time you see it, but we're going to have a whole week's worth of time to spend on it. So we're going to try to give you a lot of different ways to think about it and different problems to see to kind of help you do it. And I think once you do get your head around it, it turns out then you'll discover how infinitely powerful it is, that there's kind of a simple idea in it, right, that once you kind of fully get your head around, you can explore solve lots of different problems using this just one technique again and again and again. So it itself is a little bit mysterious at first glance, but then once you kind of master it, you'll be amazed at the kind of neat things you can do with it. So it is certainly what I consider an indispensable tool in a programmer's toolkit. It's the kind of problems you can solve using the techniques you have so far is fundamentally limited, right? And then part of what we need to do in this class, right, is expose you to these new ways of solving harder, more sophisticated problems that the old techniques don't work for. One of the cool things about recursion is it actually lends very simple, elegant, short solutions, right, to problems that at first glance seem completely unsolvable. That if you can formulate like a structure for to solve recursively, you'll discover that the code is not hard, it's not long to write, it's not tedious to write. The tricky part is figuring out how to express it, right? So it's more of a thinking puzzle than it is a coding puzzle. And I certainly like thinking puzzles as much as coding puzzles, if not more. The general sort of idea is that you are going to try to solve a problem instead of sort of breaking it down into component tasks like, well, if I need to make dinner, I need to go to the store and buy things, and I need to come home and chop them and get the recipe, that you think of what your standard decomposition is all about, breaking down your tasks into A, B, and C, and D, and then you add them all together to get the whole task done. That recursion has this kind of very different way of thinking about the problem, which is like, well, if I needed to get task A done, and I had task A prime, which was somehow a lot like the task I was trying to solve, but it somehow was a little bit simpler, a little bit easier, a little bit more manageable than the one I started out to solve. And if I had that solution, so if somehow I could delegate it off to some minion who works for me, and then I could use that to solve my problem, then my job would be made much easier by using that result in solving a similar problem that's a little bit smaller. Okay, that seems a little bit wacky, right? Let me give you sort of an example of how this might work. So your standard problem, I said, yeah, it's like, oh, you do these dissimilar subproblems. Let's imagine that I had this goal where I wanted to survey the Stanford student body. And I don't want just like a haphazard, most of the people involved. Let's say I really wanted to get input from every single person, right, on campus, right, whether they think having cardinal as your mascot is a ridiculous choice or not. So let's imagine I really want to hear from all 10,000 students. Now, I could stand out in White Plaza with a big notepad, right, and try to accost people and sort of work my way down the list, and then I'd be there for eons and never solve my problem. Instead, what I decided to do is I say, well, I'm going to recruit some people to help me, because I'm lazy, as we've already established. And I would like to get some other people to join in my quest to answer these burning questions and to solve the survey. So what I do is I round up 10 people, let's say. And I say, would you help me? And I decide to divide the campus into kind of 10 partitions. And I say, if you could survey, all the people whose names begin with A, B, and C, that would really help. And if you could do the D, E, G's, and if you would do, and if I divide up the alphabet that way, give each of them 2 or 3 letters, and I say, and if you would go get the data, it'd be really easy for me to do my job then, right? If I just took all their data and just coded it, I'm done. Well, being the kind of lazy person I am, it's likely that the 10 people I recruit would have similar lazy qualities, because lazy people hang out with other lazy people. And so the person who was in charge of ABC, if the first thing they do is turn around and find 10 more friends, and then they divide it up and say, could you do the AA through AM and so on? If they divided into these pools, right, of 1/10 of what they were responsible for, said, you can go get the information from these people. And if they did the same thing, so if everybody around the road, we started with 10,000, now each person had 1,000 to survey, they asked their friend to do 100, their friend asked 10 people to do 10, and then at some point the 10th, the person who has 10 says, well, I just need to ask these 10 people, right? And once I get their data, we don't need to do anything further. So at some point the problem becomes so small, so simple, even though it was kind of the same problem all along. I just reproduced the same problem I had, but in a slightly smaller, more tractable form. But then I divided it around, divide and conquer, sometimes they call this, to where I spread out the work around a bunch of people to where each person's contribution is just a little part of the whole. You had to find the 10 volunteers underneath you and get their help in solving the problem, but nobody had to do too much work. And that's kind of a really interesting way to try to solve the problem. It sounds like a very big problem, right, of surveying 10,000 people, but by dividing and conquer, everybody has a little tiny role to play. You leverage a lot of people getting it done, and there is this self-similarity to it, which is kind of intriguing to think about, that everybody is trying to solve the same problem, but just at different levels of scale. And so this idea, right, applies to things like phone trees, where, rather than trying to get message out to everybody in my class, it might be that I call 2 people who call 2 friends who call 2 friends until everybody gets covered, right? That nobody does the whole job, everybody just does a little part of it, right? That sometimes you'll see in these fractal drawings where there is a large leaf, which when you look closer actually consists of littler leaves, right? Which themselves are littler leaves, that at every level of scale, the same image is being reproduced, right? And the result kind of on the outside is something that in itself, if you look deeper, has the same problem but smaller embedded in it. So it's a pretty neat sort of way of solving things. I am going to tell you a little bit about how the code looks, and then I'm not going to be able to show you much code today. I think it's actually even better to show you this code on Monday when we can come back fresh. But that it involves so we're looking at functional recursion first. And functional recursion is taking some sort of function that takes some input and returns an answer, returns non-void thing that comes back. And we're going to be looking at problems where you're trying to solve this big problem, and that if you had the answer to making a call to yourself on a smaller version of the problem, maybe 1 call, maybe 2 calls, maybe several calls, that you could add those or multiply those or combine those in some way to answer the bigger problem. So if I were trying to solve, this campus survey, having the answers to these smaller campus surveys gives me that total result. And so you know what, I really should not try to do this in 2 minutes. So what I should do is just tell you on Monday. We'll come back and we'll talk about recursion, and it will be a recursive week. And meanwhile, work on your ABT or homework.